and she was awarded a Qualcomm Innovation Fellowship in 2020. So Angela, thanks for joining us, and when you want.
Yeah, thanks for the kind introduction, and it's my great honor to be here. Okay, so today I'm going to talk about a paradigm shift for the perception and prediction pipeline in autonomous driving. So let me just zoom in the screen. Okay, great. So as everyone knows, that today people believe perception and prediction are very important components in the autonomous driving stack. So what that exactly perception and prediction pipeline means? So here I show a very simple paradigm here, include the key modules such as sensor data, detection, tracking, and trajectory forecasting. I mean, there are so many other modules I didn't put here, but these are kind of the key module people use for object recognition, perception, prediction. And then people mostly view detection and tracking as a perception and trajectory forecasting for the prediction, right? Okay, so now let's just briefly go through each of the individual module. So first, for the sensor data, the most or two most common sensors people are using today are LiDAR and RGB, where the LiDAR is more like a 3D format in a set of points, and RGB is more in a 2D pixel format. And then people just pass through the data into detection module, and you will get a set of 3D bounding boxes like this, shown on the right. These 3D bounding boxes are kind of the most popular format people are using. And although there are some other representations like key points or skeleton whatsoever. And then once we have the detection, we just pass through a tracking module that will give you association across time for each individual objects. So that results a set of trajectories for each objects. People can use it for prediction into the future. So that will be the kind of the responsibility of the last trajectory forecasting module. With these predicted trajectories, you can now reason or do your planning for the eager vehicle, right? Because you have think about what other agents will behave in the next few seconds. Okay, great. So that's the standard pipeline. And so now I'm going to discuss what kind of state-of-the-art efforts that people have put into this pipeline or trying to improve trajectory forecasting module. And there are so many progress I couldn't just cover everything here. So there are just two key aspects I will introduce. One is the data sets. So it's going to be bigger and also multimodal. So what does that mean? So here I show a figure that is copied from the Waymo paper. And you can see that in the kind of the green rectangle here, people trying to label more and more objects in the data set, right? So that object can be used for training, detection, tracking, and trajectory forecasting. And also for the scene and number of hours, LiDAR frames, and also number of images, they are also become more in terms of the number of frames, right? So that's all good. People use it to improve the model based on the better data. The other important aspects is that people are trying to generate data sets with multiple futures, right? The future is uncertain from our humans' perspective, right? We always don't know what exactly is going to happen in the future, but we can kind of guess there are kind of a few possibilities there. But in reality, or in the real world data set people collect, such as Waymo data set, KD data set, right? There's only a single ground truth future, because only a single future actually happens. So that's what we record, right? So we can do this in simulator by just resetting the world and pass through different actions for each actor. So that will give you multimodal ground truth. So that's good. And the other important aspects is people trying to add more site information to the model. So that includes different things. So first of all, let's just look at this graph neural network, where people use this new technique, or actually it's not that new, but trying to be, it is kind of getting more and more popular in recent years. And people use this graph neural network to model the social interaction between agents, right? So given each individual features that is extracted for each person or each vehicle independently through a feature extractor, they can just model edge relationship between agents. So that basically consider how behavior of one agent will affect others, right? This is kind of pretty common technique right now. And the scene map or the rasterized map is also very important information people used to help predict which lane or which road that the vehicle will going to move in the next few seconds. Because once you know the road structure, that's going to be much easier for trajectory forecast, because you will not predict let's say out of road trajectory, for example. I mean, that's not common, but sometimes it also happens, right? So this is also one set information people are using. So the last one I'm going to talk about here is this work from Uber ATG, I guess last year. So most of the previous work, they are trying to develop a better individual module in the pipeline, in the perception prediction pipeline, right? Let's say a higher accuracy detector, or more temporal consistent tracker, or let's say a trajectory forecasting that consider behavior of other agents, right? But different modules are still separately optimized, right? So each module don't know how exactly other module is being optimized. So that will lead to like a couple of disadvantages. And then the work that people tried before is to jointly optimize everything in a single pipeline, right? So this basically means that you propagate the gradients from the last module, the end module, like all the way down to the previous upstream modules. So hopefully they will give you a much more consistent results across different modules, because every module is not optimized for the same or the end goal, right? So that gradient information is passed all the way down. Yeah. So that kind of highlight of some progress in the recent years, or especially in the last 2 years. And there's so much more progress that I cannot cover here. But one thing that is obvious is that we do see a lot of progress in each individual modules, but the overall pipeline looks the same, right? If we just look over all of the work, it's always going to be detection, then tracking, then forecasting. I mean, sometimes you add some additional module on the side, but the order of the entire pipeline kind of looks the same. So the key question I'm going to ask in this talk is that, is there any possibility to improve the pipeline, or let's say some alternatives of the order of this pipeline that exists there, right? So that basically leads to this diagram again. So this again shows this standard order of pipeline, perception and prediction pipeline. So we're wondering, is the last place here the best place to put forecasting module, right? Or the prediction module. So some simple question we can ask, can we do prediction here, right? Like before tracking, this looks fancy, but actually this is possible. And we have a recent accept ACRA paper that is doing exactly this, but that work I'm not going to discuss today. So the other question is that, can we do prediction here? This is even more crazy, right? Because it's doing it the very beginning. So the answer is yes, again, to this question. So that leads to the forecast and detect pipeline that I'm going to introduce later. So basically, our pipeline trying to inverse the order of the forecasting and put it very upfront, right? So I would say it's quite different from all the previous work, but individual kind of key points is the same, except for the forecasting, which is the key thing I will discuss later. Okay, so here, look at this figure again. This is standard pipeline. You have detection, tracking, and forecasting, right? So the detection, tracking give you some trajectories of each object, and you just forecast into the future. So that's basically represented by these dotted lines for each objects. And then what's offered in this new forecast and detect pipeline is something different, as shown on the right. So here we do the forecasting at the beginning, right? But what do we have at the beginning? We only have the sensor data, right? So that could be LiDAR point cloud or video data, like I said before. Right, with this latter data, what we can do here is forecast point cloud, right? So that's the only thing we can do because we only have point cloud here, right? So that will give you point cloud of the future frames. And then once we have this point cloud, the predicted future point cloud, we can do the same detection tracking on top of it. That will give you trajectories of object in the future frames, right? So if you look at the result of these two pipelines, they are very equivalent to each other, right? Because again, on this new pipeline, you are getting the trajectories on the future frames that is equivalent to the trajectory predicted given the past trajectory, right? So we can use this kind of property to compare these two pipelines because we are getting the same results at the end, although the paradigm looks very different. Okay, so yeah, so that's the main difference. We move forecasting up front, and we forecast at the sensor data level, not object positions, right? Okay, so the figure looks maybe boring, so let's just look at some videos. So here is what we can do with this new pipeline. So since we do forecast and detect pipeline, we first need to forecast the point cloud. So here I'm showing the point cloud color as blue is basically the predicted point cloud for the entire sequence, right? So I'm just beginning at every let's say 10 frames and then just concatenate all of the predicted frames into a single video, right? So that's the predicted point cloud, and you can see some original real LiDAR point clouds at the beginning. So that's what we use for prediction, and then all of these boxes on top is the tracked objects. When we apply detection and tracking on top of these predicted point clouds, I mean, we kind of fine-tune the detector on this new data because this predicted point cloud looks very different from the real world raw sensor raw point cloud data, right? So once we fine-tune, that's what we got. And then you can use different kind of detection and tracking algorithms, obviously. So we just use some standard techniques for the detection with point arcing. For tracking, I used AB3D MOT developed by our lab. Yeah. So you can see that by using some simple detection and tracking algorithms, we can get fairly good tracked objects on top of these predicted point clouds. So what this means is that our predicted point cloud preserves object information, right? Right, because if we don't preserve such bumps or these objects with blurry shapes, right, there's no way you can detect and track on top of it. So the detector and tracker capture these information during training, and then they can achieve detection and tracking on top to get these trajectories. And again, this is equivalent to result you can obtain from standard perception prediction pipeline, right? It's just in a different form. If you want to get ground positions, you can just extract them from these bounding boxes. That's fairly easy. Okay, so that's what we can do once we have this new pipeline. And I will show more results later. But now let's look at some more kind of properties or the advantages of this new pipeline. So first, if you look at this point cloud forecasting module that we do at the beginning, it does not require any human annotation for it during training, right? Because now the supervision signal you need is just the point cloud in the future, right? You don't need object trajectories at all. So that basically is the point cloud data itself, and which is prevalent nowadays in all of the modern data sets. I mean, the companies like always have like almost unlimited point cloud data collected by their self-driving car, but they don't allocate all of them, right? Because there's no way you can allocate all of them. But even for public data sets, you already get tons of point cloud data for KD using Waymo, for example, right? So all of this key or all of these advantages come from the key for the new task, which we call sequential point cloud forecasting, or SPF. So it's not, I mean, this task is kind of new, but not completely, I would say, novel, because there are a lot of related work in the past. For example, video prediction. Lala is doing almost the same thing, but use different data, right? Basically the RGB video. And also there's some work doing occupancy grid prediction, right? It's a different format or different process data of the point cloud, right? So I mean, this kind of forecasting point cloud is not completely new, but we're doing it for this new pipeline, this SPF square pipeline, which we also call it forecast and detect pipeline. Okay. Yeah. So once we have these advantages, there's a key difference is that our pipeline can scale the performance with more unlimited and also unenabled data, right? Which is the point cloud. So on this figure, I'm showing a kind of a small experiment we've done in the core paper that demonstrate that the performance goes up when we have more data. This is kind of obvious, but it's especially more true in our case because we can have more unenabled data for point clouds rather than labeled object trajectories. So specifically for these two figures, you have the orange line showing for the Earth movers distance and the blue line for the chamfer distance matrix. People are mostly, these two matrices are kind of popular in 3D computer vision, where people evaluate like 2 point clouds and how accurate one is compared to the other, right? So the numbers are lower is better. So we are kind of getting better performance when we add more unenabled data. So in this experiment, I'm using all of the training samples in the KD datasets, which is about more than 100 sequences. This is for KD raw, not KD objects or KD tracking. But obviously, you can combine with other datasets like NewScenes or Waymo, whatever, to do the same experiments. But there might be some issue, for example, sensor discrepancy between each dataset. But the goal here is basically just showing, okay, you can just scale the performance with more data. This is easily done in the company where you have much larger data set to execute this. Okay. So we've talked about the sequential point cloud forecasting task and also the advantages of it. So let's just now look at more closely about how exactly it's doing, right? So again, the task is trying to predict the future point clouds given a sequence of past point clouds, right? And it's different from trajectory forecasting task we've seen in the past, where it's look at only foreground objects. But our SPF task is looking at the entire thing. So basically, it means that you want also predict background information, not just foreground objects, right? And also on the other dimension, if we compare to the very popular point cloud generation or point cloud reconstruction task, where people mostly focusing on indoor objects, right? So in that sense, they're dealing with a much smaller scale objects or much smaller scale point clouds. For example, a few thousands of points. But in our case, it's much more challenging because the entire data we're going to process is like 1.5 millions of points. So this basically includes 10 frames or 30 frames of the point cloud, and each point cloud is about how much is it? 150,000 of points, about that size. That's captured by the Veldheim LiDAR, but you can use other LiDAR as well. So it's much larger scale, right? And formally, we can just define this task here. It's fairly simple. At each frame, you have just a set of XYZ points, right? And the total number of points varies across frame, but you get very high number of points at every frames. And the outputs, you're dealing with, you're trying to predict another set of point clouds, which is noted as F here. And there's also a set of points for each frame, right? And what we're trying to do is to learn a function that maps from P to F, from the past point cloud sequence to future point cloud sequence, right? So that's the model I'm showing here. Okay, so the key question here is that how we can learn an effective representation from these large-scale point cloud sequences, right? So that's the major difference compared to the prior related task. And we're proposing a very simple baseline in the core paper, which we call as FCLSTM autoencoder model. It's a very standard model people use for time series forecasting task. Right, it includes 4 modules. So first, you have this frame-wise point cloud encoder shown in the blue, right? So that will include each individual frame of point cloud. And then you have this LS team in the middle doing temporal modeling. And afterwards, you decode the LS estimated feature to the point cloud in the future that you want to obtain, right? And nodes, we can just simply use chamfer distance between the predicted point cloud and ground truth point cloud. Okay, so again, here I'm showing some results. So this is for the point cloud forecasting task only. So there's no forecast and detect pipeline. So on the top, you can see this sequence of ground truth point clouds. On the bottom, shown as blue, you'll see this prediction of point clouds from our model, the SPF net. So overall, if you look at these 2 sets of point clouds, they are looking very differently, actually, I would say, right? Like globally, the red point cloud definitely include more information, better structure, and some small objects, which are not kind of encoded in our predicted point cloud. But one thing to note is that if you look at the predicted point cloud from our method, for the large object like vehicles, it's actually doing a pretty good job, right? So if you look at all of these bumps, that's basically the predicted objects or the object predicted in our point cloud estimation or in our point cloud prediction. So yeah, there's a lot of vehicles on the side road. So you can also see it here in the predicted point clouds. So this kind of good property that we have in this SPF net is the reason that can support this forecast and detect pipeline, right? Because if our model ignores those objects, there's no way you can do forecast and detect pipeline. Okay, so I think this is a good time to pause here to see if there's any question so far about the forecast and detect pipeline, also about the sequential point cloud forecasting. If there's no question, I will just move forward because, yeah, it's kind of a good cut here.
I'm not sure if you will talk about it next, but if your goal is to do tracking or detection, of course, like you don't have annotated data, right? But can you do something to avoid like caring about all the points in the point cloud and maybe focusing on points that are more object like?
Yeah. So that's a good point. I mean, a simple way to do it is, let's say during training, you have the chamfer distance loss, right? We can put weights on each individual point when optimizing the network. And then basically we put weights higher on the points we care about, let's say optics, right? And we put weights lower for the other irrelevant object. I mean, that's definitely possible to do. Actually, we tried it, and it's doing exactly like you said, better performance for the object. But something interesting is that when you look at the object, when you look at point cloud predicted from the network, it's doing much worse job at the global structure. Basically, the point cloud you get will look much more horrible than this. So basically, the between the global structure and local information is fighting against each other. So basically, the representation we use right now isn't powerful enough to kind of handle well for everything. So that's why it kind of can only do a very good job on something, but not other things. Yeah. So it's a trade-off. I mean, if we just care about foreground objects, then yeah, that's definitely a way to do it. But if we also want to get very good realistic and like looking point cloud, so I mean sometimes people also do, let's say, point cloud segmentation or point cloud panoptic, trying to get information for all of the background points. And then some people believe those background information is also critical. So in that sense, I mean, we shouldn't ignore the background information that much, I think.
Makes sense. Thank you.
Sequential, can I ask a question?
Yeah, of course.
Yeah, I'm wondering like how long can you predict into the future without seeing a very obvious drifting? The reason I'm asking that is especially how it compared to like object-centric models where the objects are being abstracted up prior. And because the dimension is very high dimensional, like when you compare with like you have several objects represented as graphs, and also if you are also directly predicting the raw sensory data, which contains a lot of like noise and backgrounds, which it is good to predict those, but that also introduces a lot of uncertainties.
Yeah, exactly. So first of all, let me answer your question. How long can we predict? So we experimented a few different variants, like 2 frames, which means 0.2 seconds, and 10 frames, that means 1 second, and 30 frames, that means 3 seconds. But unfortunately, because the memory constraint on 2080, if we do 30 frames, then we have to skip some intermediate frames. So basically, you're predicting, let's say, frame 0, frame 3, frame 6, frame 9, not seconds, but you're still predicting 10 frames, basically. So there are some tricks we try to kind of reduce the memory constraint because there are too many point cloud you need to process. But yeah, so overall, right now we tried at most 30 frames. And an observation we got, which is quite obvious, the longer we predict, the worse performance we get, especially for the 30 frames, right? And also all of this model is deterministic. Oh, sorry, all of the results I'm showing so far is deterministic, meaning that there's no multimodal into the future prediction. So if there's uncertainty, there's no way you can capture it by this model.
Oh, sorry, I have another question related to this, this paradigm. So you're saying you're doing like point cloud prediction, right?
Yeah.
So I wonder why you choose to do like point cloud generation instead of like predicting the motion of the points, right? The reason why I'm asking is because if you predict the motion of the points, then a large portion of the point clouds are background and they all have the same 3D motion. So wouldn't this be much easier? Because then the task will be much lower dimension because you just need to, for instance, have a motion for each foreground object and one motion for all the background points. And I just wonder, yeah, and because if I look at your results, it seems like lots of structures are a bit kind of disappeared, right? For instance, the word kind of disappeared. So I wonder what's the rationale of directly generating the point cloud instead of like producing the motion and then warp it.
Yeah, very good question. So first of all, to predict the motion for each point, there is actually, I mean, this is pretty related to SymFlow, right? So that's what SymFlow does, but the SymFlow is only doing for 2 frames, or so far people are mostly doing for 2 frames. Your estimation motion, your estimated motion for each point, for just between 2 frames. So we can extend this to more frames, let's say 10 frames or 30 frames. The main thing or the main bottleneck we were worried about is the correspondences. So when you predict the motion, you will need the ground truth motion for each point, for example, right? And then because this is LiDAR point cloud, at each frame, the point is sampled differently. So there's no hard correspondences between each point across frames, right? So if you don't have these correspondences, that means, or if you don't have this perfect correspondence, you can definitely get some rough estimate correspondence, maybe. You don't have perfect motion. And if you don't have perfect motion and you predict for long horizon, let's say 10 frames or 30 frames, you will get, you will need to run training probably, right? Because the correspondence is not accurate, and then because of the time shift or the motion shift accumulation across 30 frames, it's probably going to be doing some run training for the motion, right? So does that answer your question?
Okay, thank you.
Yeah, actually, we received a review from ECCV about exactly the same question, and then they are suggesting a solution which is using simulator. So they're asking us, okay, yes, we don't have exact correspondences in the LiDAR, in the real world LiDAR point cloud data, but we can have it in the simulator potentially, right? So in the simulator, What about we sample exact same points for either foreground or background, and when generating the point cloud data, and then because we have the correspondences, we can have the motion, right? So
yeah, so I was thinking it's just like you don't necessarily need the correspondence to get the ground truth a lot of times, right? For instance, for the background motion, you can just compute it with the ego car. And for the, and for the bounding
exactly.
labels.
Yeah, but that's only accounts for the vehicles in the background. But how about the pedestrians?
For deformables, that might be an issue. But I was just thinking, why not? Since you are using transfer distance loss. Okay.
Thanks. I totally understand it. Actually, we were trying to do this at the beginning before thinking about this point cloud forecasting directly without correspondences, because later on we realized, okay, this problem is easier in the formal formulation because we have the point cloud data already. There's nothing we need to process in terms of the data. But I do agree. I mean, doing the motion estimation probably going to make the task easier, although you probably need to prepare the data in a more serious way, either for deformable or non-deformable objects. Yeah, because pedestrian is definitely an important component we need to care about in autonomous driving, so we cannot ignore it at all. Okay, great. So we kind of passed 40 minutes. Let me try to speed up. Probably I don't have time to go through everything. So maybe let me just skip this part. So this part basically illustrates the encoder we use for each LiDAR point cloud frame. So it's fairly easy. So basically what we are doing is given point cloud data, we convert it to a range map. Some people may already familiar with it. As it's nothing but a spherical projection of the point cloud. So the x-axis accounts for the azimuth, and the y-axis accounts for the elevation. So that's what you get by projecting it as shown here. And then later we just use the 2D CN to get the hidden feature for each LiDAR frame. Yeah, and then the LSTM is fairly simple. We just use sequence-to-sequence model, right? And loss function, chamfer distance loss, and one. So I will basically skip this part because this probably a little bit boring. So more interesting part I'm going to show is this. So this is the result we get by applying detection on the predicted point clouds, right? So when we do the forecast and detect pipeline, first when we forecast the point clouds, the next step is doing the detection, right? And then if we want to compare how good the detection is compared to ground truth, so this is the way we do it by visualizing how exactly the detection on the predicted point cloud align or match with the ground truth bounding boxes, right? So basically here, the green shows the ground truth bounding box, and green shows the detected bounding box on the predicted point clouds, and yellow shows the ground truth bounding boxes. And if you look at the results closely, they actually matches with each other quite well, but only for I would say like closer range. Like there are some objects that are too far to be captured in the predicted point clouds, and those there's no way you can detect it. But for objects that's entering into the predicted point clouds, the results looks quite good, I would say. Yeah. So this is the first step of the forecast and detect pipeline. You do, the second step, which you do detection. And then the next step is where do tracking on top of the detections, right? So again, on the top, I show the prediction. On the bottom, I show the ground truth. So on all of this is a sequence of 4 frames that are sampled at a low overlap of, at an interval of 5 frames, if I remember correctly. And although the counter will be different for the top and bottom because the absolute identity number is different for objects in ground truth and prediction. But overall, if you look at the results, the location or the tracked identity in the prediction and ground truth, they looks quite similar. In fact, on this sample, it looks perfect. But I mean, there are also many other samples that are not that perfect. So which are the issues we are trying to address. I will show some of them later. Yeah. And if you want to see a video, so this is how it looks like. Right. Again, we're showing the same video sequences, but here is showing the color bounding box rather than all the detected bounding boxes with the same color. So again, like I said before, this forecast and detect pipeline is only possible if the predictive point cloud can preserve the object information, because otherwise there's nothing you can track or detect on it. Okay, great. So if there are no other questions, I'm going to talk about some limitations and further techniques we use to improve this sequential point cloud forecasting task. Okay, so the first limitation we have is that the predicted point cloud an object does not look real, right? It's missing a lot of details, like mentioned by Rachel before, right? So there are walls and there are pedestrians, and there are some, I don't know, traffic lights, which does not included in the predicted point clouds. I think the main thing that our model preserved quite well is the objects. It's a large object like vehicles, right? So all of these details are missing. And on the right, I'm showing video sequences, including the pedestrians, right? So if you look at the ground truth, there are actually quite a lot of pedestrians they are walking, right? But none of them is captured in our predicted point clouds shown on the bottom. So this is a severe issue, right? Because we can't just ignore those small objects during driving. They are also very critical when we do planning. And the other important issue is that all of the predictions so far we can do is deterministic, although we know the future is uncertain or multimodal, right? Let's say at a intersection, there's no way you are 100% sure if the vehicle is going to turn, or if other vehicle is going to turn left or turn right without any signal or information, right? So the future is uncertain and multimodal, but our model currently cannot do it. So in that sense, I'm kind of introduce, or maybe just one of them, I don't know, give me time, about how we're going to improve this sequential point cloud forecasting task. So the first is stochastic sequential point cloud forecasting with sequence VAE. And the second work is to learn fine grained point cloud prediction with pyramid LSTM. So maybe let's just look through the second work first, in case there's no enough time, because the sequence VAE model probably is going to be a little bit more involved. Okay, so for the second work, yeah. So again, this slide shows the issues we had before. We are missing details, and we cannot preserve small objects like pedestrians, right? So one hypothesis we had is the hidden representation is compressed too much or is not that powerful to capture everything. This also mentioned before. And there are a lot of straightforward solutions that we can try. So first of all, we can kind of improve the SPF net we had before by increasing the dimensionality of the hidden features or adding more fine-grained intermediate feature maps to represent what we can encode in the latent state. For example, we can increase the one-dimensional feature in the hidden LSTM state to two-dimensional hidden map, right? This is a very common technique people use. And also we can replace FC LSTM to convolutional LSTM, which are abbreviated here as CLSTM, right? So this is quite common. The other thing we did is we can use better or stronger backbone, right? So previously we just used a series of, or actually just 4 convolutional layers plus batch normalization and leaky ReLU. So what about we use a much more complex model like Darknet 53, which is doing like impressive results on point cloud segmentation, right? So here on the right, I'm showing this dark-clad 53 model, including its encoder and decoder. And there are some skip connections, which are very important, especially for this dense prediction or high resolution prediction task, where in this case, it's point cloud segmentation. Okay, so once we have those things included in our SPF-led, this is what you get, right? Again, we have this sequence-to-sequence model, but we replace the encoder with dark-clad encoder and decoder with dark-clad decoder as well. And we have this convolutional LSTM, and we have this skip connection between encoder and decoder that will hopefully help increase the sharpness or the information in the decoding stage, right? However, something bad happened, which is the training of this model doesn't really converge very well. So this is what we tried at the beginning. And we thought about like what's the issues, right? I mean, there are potentially many issues at this stage of the model. But one of the most important issue we realized is the feature synchronization issue. So again, if you look at this model, for every frame that we're predicting, the hidden feature that is shown here after passing the convolutional LSTM is at t equals 2, right? Because it's already propagated through the LSTM and get to the next frame. However, the feature that we do skip connection here, shown in the green, is still at the time equals 1, right? Because this is directly obtained from the lower level features of the encoder, which is encoding the point cloud at t equals 1, right? So these two features are at different time steps, which causes the training kind of unstable, because the decoder trying to combine the feature at different time step and use that to decode the point cloud at t equals 2, which is problematic. So once we realized the issue, what we did is a pyramid LSTM. Or essentially, this pyramid LSTM is a spatial hierarchical LSTM, and each of the hierarchy operates on the different feature scales. So this may look a little bit abstract. So what does it mean is as follows. So here I'm showing this figure again, which has the exact same architecture as before, but we remove the connection, which is we remove the skip connection, which is problematic. So what we're gonna add here is an additional convolutional LSTM that connects the features from the lower level during this skip connection, right? So before you do this skip connection, you pass these lower level features into the convolutional LSTM, and then you add into the decoder, right? So we can do this again for the even lower level features and use an even different LSTM. And all of this LSTM 1, 2, 3, they're operating at different scales because the heat map you're processing is at different sizes. And again, we can add this temporal dependency for each LSTM. So that will kind of conclude this pyramid LSTM approach we are using. And not surprisingly, this model converges much better compared to these the previous model without this pyramid LSTM. And there are a lot of quantitative improvements on different metrics. Okay, so here is what we can do once we have this pyramid LSTM. So once again, we're comparing the SPF-net and pyramid LSTM on the left and right. And here, one interesting thing we did is we are trying to colorize each point to indicating the error. So basically, the point that's with red color, meaning that this point has a large chamfer density error, but the points with cyan means that it has a lower chamfer density error. So with this kind of colorization, it's very easy to compare between the point cloud prediction from SPFnet or from parameter LSTM, because on the right, you will see much less number of red points compared to the prediction on the left, where you see much more red points. And also all of the wall structure or the roads becomes much more clear than the model that we use for SPFnet. And one other kind of observation we had is that when we're trying to predict the point cloud containing pedestrians using SPFnet, it doesn't really work that well, right? So we're trying to do this experiment again, but using the parameter LSTM. If you look at this prediction down here, there are kind of small motion of points that we predicted, or a small set of points that we can predict representing the pedestrian in the prediction, right? So these basically represent or means that our model with parameter LSTM can now enable the forecast and detect pipeline on the pedestrian level, or we can preserve like small objects like pedestrians in the predicted point clouds. Yeah, so I think that kind of concludes the main work I'm going to propose today. Yeah, I'm going to skip the first work because of limit of time. So yeah, so this is the few last slides. I think the take-home message here I want to emphasize again is that innovation is not possible to happen at the module level, which is done in a lot of prior work, but also possible at the pipeline level, right? We're kind of propose a new paradigm here to address this trajectory forecasting task. And also this new task, this new pipeline, that's only phase 2. Yeah, so I kind of skip this point. So this simple SPF-led baseline can preserve information for large objects but lose details. So later we propose this parameter LSTM that can increase details on global structure and also small objects. There are tons of visualization we have for this point cloud prediction model, especially in the newest model we have. Yeah, so if you're interested, we can discuss more offline. But overall, we believe the newest model we have kind of preserve much more details. Yeah, and there are a lot of open questions. For example, how do you scan to produce more realistic results? Is the representation we learn useful for other tasks like planning? We're kind of doing this right now, actually, collaborating with some other university, and also the how to combine the sequential point cloud forecasting with video prediction, right? So video prediction is quite popular, but I don't think right now people are using video prediction or fit this video prediction task into the forecast and detect pipeline. Although camera image is kind of very important input modality to trajectory forecasting. So we can combine them into the same pipeline as well. And also predict sequence of point with correspondences or predict motion of points, like mentioned before, right? So all of these are open questions we're trying to address later. Yeah. Okay, so that's it. Thanks everyone for listening. And at last, I would like to kind of advertise 2 of the workshops we're organizing recently. So one is the IGCAD workshop on the autonomous driving, and the other is ICV workshop for multi-agent interaction and relational reasoning. So welcome everyone to attend. So that's it for today, and thanks everyone again.
Thanks a lot for the great talk. Yeah, I guess we have time for 1 or 2 questions.
Mm-hmm.
Can I ask a question?
Yeah, of course.
Can you comment a little bit on the latency of the pipeline? Because latency is important for reaction time of the vehicle, autonomous vehicle, right? So I was wondering if you can comment a little bit on latency of the two pipelines, the conventional and the new one.
Yeah, I would say For the conventional pipeline, the latency varies a lot depending on which model you use. So it's really hard to have a, I would say, a unified or a universal latency that I can comment. But I would say the N2M pipeline, for example, developed by Whooper ATZ, maybe the fastest. I'm not sure because you have a single model, a single N2M pipeline for all of the modules, right? Instead of you just run detection and run tracking and then run trajectory forecasting, where each of the module takes a very long time, especially for detection. But for our model, basically the detection and tracking is the same as the conventional pipeline. So there's no difference at all. So the main part is the same point cloud forecasting. Right now, I would say it's definitely slower than the trajectory forecasting component in the standard pipeline because we're predicting much more things. So normally, I think we can do it at 10 FPS, not real time. So that's what we can do right now. But for the, let's say if you do trajectory forecasting in the conventional pipeline, you can use a very simple model like just LSTM, right, to predict motion. Then that will be very fast. Or you can just use Karma filter, for example. There's no deep learning at all. That's even faster, right? So it depends on the model you use for the conventional pipeline about how to do trajectory forecasting. But for our model, it's definitely a heavy model so far because we're predicting a very large point cloud sequences.